Good afternoon, drone pilots. Today's lecture will be about autonomy and AI in drones. First section is autonomy, and the second section will be AI. So the first kind of autonomy is already well known to you and will be the requirement to graduate from this course. As a requirement to graduate from this course, you need to build and fly a drone that flies a completely pre-programmed waypoint mission. It takes off, flies to the waypoints, and lands completely without any human input at all. And this is autonomy. So you will be doing that by the end of this quarter. This is actually built into ArduPilot, as you know. You've been learning ArduPilot all quarter, and you'll get to see it in action when we go fly. And it's built into the code that you can pre-program the waypoint missions, and it'll fly them if you put it into auto mode. So this is a kind of pre-programmed autonomy where it doesn't matter what's going on in the universe. The drone does whatever you told it to in a pre-programmed mission. And by the way, this is what drone light shows are also. So you'll get the chance to get a guest lecture from one of the drone light show companies, but essentially what drone light shows are a set of drones that all have pre-programmed missions. They don't talk to each other. They only report their position back to the ground in case something goes wrong. But if everything goes right, it's a series of N drones that's equivalent to your 185 drone, all flying pre-programmed missions. The trick is programming them so that they're making a pattern in the sky. And the other trick is getting the GPS accurate enough with RTK so that they're not crashing into each other. So this is one simple version of autonomy. The next level of autonomy is where the vehicle or system makes decisions based on the situation that's unpredictable. So I call this situation-aware autonomy. So there's still no human input, so it's completely autonomous, but the actions are based on what environmental and sensor and other data is given to the system that's not predictable from the beginning of the operation. So one example of that, which is already also programmed into ArduPilot, is a package called ADS-B avoid. So we discussed ADS-B is required by most, but not all manned aircraft as a transmission of their lat, lon, and altitude that can be read out up to 100 miles away. So if you have an ADS-B receiver on your drone then can be automatically aware of the location of those manned aircraft that are transmitting. So within ArduPilot, already almost 10 years, there's been a subroutine that you can enable, which will turn on this ADS-B avoid set of actions. And if the drone sees an airplane through ADS-B coming toward it, it will take an avoidance maneuver. It could land, it could rise, it could fall, it could just report back. It might move perpendicular to the direction of collision to avoid the collision. So this is available already in ArduPilot. We actually, in my lab with the senior design student, developed a similar version of that, which is a fork of ArduPilot, where the drone would autonomously avoid other drones that it detected via remote ID. And this was a fork of ArduPilot, and we demonstrated it with one drone coming close to another drone, and it moved out of the way. So these are situational aware autonomous actions that are available in ArduPilot and demonstrations of situation aware autonomy already. Now, to enable these, you have to write the code in ArduPilot, compile it, and download the binary to your flight controller as you've been doing all quarter. And that requires some work. And it would be nice if you didn't have to compile a million lines of C code every time you wanted to implement a new autonomous feature. So the next level of autonomy is going up in the system where you're not flashing it, or so you're not compiling the autonomous behavior into a binary that's set once you've flashed it, but you're scripting from a higher level language. So this could be also programming in C. Scripting is using a program that runs as a language like Python, which is interpreted, it's not compiled. So that means that you don't have to have a compiler if you want to write a new program to do something. So there are many scripting languages. Python is the most popular and most widely used, so we'll focus on that in this class. But in general, any scripting language could be used. And in the context of drones, Python scripts can be used to send Mavlink commands to the flight controller, either from an onboard computer or from an offboard computer on the ground. So in this class, you all have Raspberry Pis as part of your kit, and you will be connecting that to the flight controller as part of one of your advanced optional exercises. And what we demonstrated last lecture was using the Raspberry Pi as basically a Wi-Fi hotspot. It would just route Wi-Fi traffic from its Wi-Fi hotspot to the flight controller, which is nice and it's convenient. However, the Raspberry Pi is a full Linux computer, so anything you can do with Linux, you could do on this computer. And so one thing you can do is download Python to this computer, download Python code, or you can even write your own Python code using the editor on this computer, and then run that Python code as a script that controls the flight controller. So that's a version of onboard computer running scripts to control the drone. And then whatever you want to do, you run as a Python script. You don't have to flash a binary, you don't have to compile a million lines of code, so it's much more flexible. Similarly, the ground-based computer can be used if the ground-based computer is somehow or other connected to the drone through Mavlink. Because Python can call Mavlink commands. That's what we talked about last lecture, and I'll talk about it in a minute. So if you can get Python to send a Mavlink command, one way to do it is through your Express LRS transmitter that you've already built and installed on your drone. And if you have Python running on the local laptop, that can send the commands over the Express LRS protocol all the way up to the drone and send it Mavlink commands directly to the flight controller. Or if you don't want to use Express LRS, you could use internet with 4G connected drone. And as long as you have an IP address on the drone and an IP address on the ground, it doesn't matter how it gets from the ground to the drone if that internet traffic is allowed. So that could be through a 4G cell phone station, 5G. It could be a Wi-Fi hotspot somewhere at Starbucks or McDonald's. It could be Iridium, Starlink, anything that can support IP protocol, then Python can call that script Mavlink to send Mavlink traffic over that internet link. So this is an example of scripting. So Python being the most popular language, we're going to focus on that. It's also most well developed for drones. And there's two packages, one called PyMavLink and one called Mav SDK. These are packages for Python. So in order to use them in Python, all you have to do is install the package, pip install PyMavLink, so it's available on your computer. And then in your Python script, at the very beginning, you say import PyMavLink. And from then on, all the PyMavLink subroutines are available to you, which package up Mavlink packets and parse Mavlink packets that are received. So we'll talk a little bit more in depth about that in today's lecture as examples. And essentially every Mavlink command that you can send or receive, you can do through this higher level Python package. So you don't need to know what the Mavlink packet protocol is in detail. Mav SDK is a higher level version of that. So it's got higher level commands, but it's a similar package that you can install from Python. Both are well maintained and very mature. So Mavlink we talked about in the past is the low-level library. It's the language that you use to send commands back and forth between drones and computers. So the PyMavlink package is on GitHub, and this is a list of some of the commands that you're going to want to use in PyMavlink. So you can wait for a heartbeat, you can establish a connection. So the very first important thing is to create a connection to your drone with this one line of code. So when you establish that connection, then you have a connection in the code to the drone, and you just say let's say it's called connection number one. You say send this command through connection number one to the drone. And then you can receive and parse Mavlink messages from the drone. You can send long and short Mavlink commands. You can arm and disarm the vehicle. You can set the flight mode. You can send waypoint points. You can receive waypoint points. You can receive the GPS position of the drone, etc. So the entire Mavlink library of all 255 different message types are all encapsulated in this Pi Mavlink package. So with that in mind, I have developed a Hello World script for you as an exercise. So this tutorial will allow you to autonomously control your drone with a Python script in the sky. And I'm going to explain this particular tutorial to you in detail, but there's many more coming that I won't have time to explain in detail. So let me just explain this one in very simple detail. You are going to, with your drone in the air, have the Raspberry Pi connected to your drone. So you all have a Raspberry Pi in your kit. And the last week I've been showing you and teaching you how to connect that, and there's lots of tutorials available. So once you log onto the Raspberry Pi hotspot, you SSH in, you have a terminal, you're running commands on the Raspberry Pi with the terminal on the ground. So we covered that last week. Now, the tutorial explains to you step by step how to install Python, install PyMavLink, write a simple script, run the script to control the drone's action. In my example tutorial, you tell the drone to land because that's the safest thing I can think of for you to tell the drone to do. So we'll look through that briefly from the canvas right now. So it's under advanced topics, under files, advanced topics, autonomy, tutorials. So we want Hello World autonomy script. There's 8 here. I'm going to discuss all 8 in today's lecture, but I'm only going to show you the first one in depth. And how many pages is it? It's 5 pages. So this is the prerequisite. This is the installation procedure to install Python. This is the script that you're going to run. This is how to run the script. This is how to, on the bench, this is how you run it in the air. So please test it on the bench first without the propellers installed. Okay, so let's look through it in slightly more detail, just so you have an idea. The prerequisites are get your drone on the internet. Any questions? Watch the YouTube videos and the tutorials or the last lectures. Now, unfortunately, the recorded lecture of me connecting to the drone over the internet didn't work because I forgot to press screen record. So if you weren't at the lecture, you'll have to talk to your friends or take the class next year or watch the YouTube tutorials that show you how to get it on the internet. So once you have your Raspberry Pi, you can SSH into it. You have to install Python. So you run these commands. You have to install various Python packages, and then you have to install PyMavLink, which is the package that interfaces Python to Mavlink. You have to install PySerial that allows Python to send serial commands. And then you have to create a script and run it. So the script is going to be called land ArduPilot land mode. And once you've created the script, you run it with this command. So it's set up so that you tell the script which device you're using, which in our case is going to be serial 0. So to create this script, you just have to edit it in some text editor and upload it to the Raspberry Pi, or you can edit it in real time by using Nano, which is a text editor, and just copy and paste this in. So here's the Python code. You just import PyMavLink, you import a couple of other commands, and then we have this wait heartbeat function, we have the request mode land function, and then the main. So the main starts, and once it starts up, it creates a connection through mavutil.mavlink connection. So master is an object, which is the connection. And you send and receive all commands through that connection. And if it doesn't work, it throws an exception. And once that's done, it waits. Once it makes the connection, it waits to make sure it has a heartbeat. And once it has a heartbeat, it tells the drone, it calls this subroutine request mode land. So request mode land simply sends this command to the master object, which is your drone. It says, make the mode ID land, and it says, tell the drone to land. This is one line of code that tells the drone to land. So all you're doing is calling three Python lines of code. One is connect to the drone, one is wait for a heartbeat, one is send the drone a command land. So try that on the bench, and you'll see it change the land mode immediately, even with the FPV monitor. And then if that works, try it in the air. So I call that hello world autonomy, because you've now demonstrated the ability to control the drone with a script. And I should probably make it explicit. Once you save that script, you have to tell Python to run that script. So when you're still logged into the shell terminal through SSH, type in this command, Python land autopilot.py with these options, and it will send the drone into land mode. It'll just change the flight mode to land, and it will land. So you're logging on, you run that script. So that's why I call it hello world, because now if you can do that, you can do anything. I'm not going to go through every single possible thing you can do with the drone. There's no way to do that. So this is just getting you the ability of running a Python script on an onboard computer that controls the drone. Hello world. Okay. And okay. So that's a way for you to run a script on an onboard computer to control the drone with the hardware and software that you have this quarter as part of your drone kit. If you want to learn more about using Mavlink to set all these modes, there is an excellent series of YouTube tutorials that show you in detail how to make the connection, what the syntax is, how to use them. And you may want to create a virtual drone in the cloud like I did last lecture and fly your virtual drone in the cloud. So if you're interested in doing more detailed Mavlink development for drone scripting, this is a good series of tutorials which goes a little bit beyond the hello world. Connect, arm, take off, movement, set you on speed. Okay. So that's the first of 8 tutorials that you have an option to do to demonstrate autonomy and AI. So we have 7 more to go, and the remaining 7 will not be quite as detailed, but I will cover them generally. So the higher level library is called Mav STK. It's got some higher level commands like takeoff and land, return to launch, set takeoff altitude. It's very similar to PyMavLink. It's a slightly higher level Python package that's also available to you. So let me go back one. So raise your hand if you're good at Python programming. Raise your hand if you've ever written a Python program. Most of you have, because it's so easy. When I was your age, we didn't have Python. We wrote a program, Hello World. We had to compile it. So it would be Hello World, and then we'd have to compile it and run the binary. So Python, you just create a text file, and then the program will interpret that text file and run it on whatever machine you have, Linux, Mac, Windows, etc. So if you want to be good at it and you want to use that for drone control, that is a method to do scripting and autonomous control of drones. And as you know, with Python, it's very well developed, and you have Python packages for pretty much everything. Of course, you can calculate pi to 1 million significant digits, but I'm pretty sure there's a Python package that will send an email. Is that true? I'm pretty sure there is. So there's Python, Xing is nodding. Thank you. So there are Python packages for pretty much anything you'd want to do, not just calculate things on a local computer, but interact with anything on the internet. Send a file, receive a file, log onto a website, download the website contents, watch a movie, create anything you want with Python. So that goes for drones also. Whatever you want, whatever you can do with Python, you can use that to decide what the drone is going to do. Now, if you want to do something very complex, you may not want to write Python code line by line. For example, if you want to build a self-driving car or self-driving drone, you may not want to write code one Python line at a time. Even if you had AI like ChatGPT to help you write it, you may not want it. So there's a higher level set of software available for autonomous systems, including drone pilots, but also land vehicles and robots in general, called Robot Operating System. So this is a much higher level, Tinker Toy level software package that allows you to find what are called nodes. So one node might be a camera, one node might be landing gear, one node might be a robot arm, and one node might be another robot. You could have lots of different robots, each being their own node. And instead of writing line by line Python code to control that node, you have a higher level scripting language within this operating system that you can plumb together graphically rather than textually. So for a review of that, see this paper that's referenced down here in Science Robotics in 2022. The most recent version is version 2. And I believe Professor Chakri's entire class next quarter is on robot operating system on robots. Is anybody taking that class? Is anybody taking it? Yes. Yes. So
I think he's offering those type of classes in the spring.
Okay, so I need to fix this. So this is a whole class in and of itself. Okay. So that's a higher level way of doing autonomous control. Now, these are open source public, but if you work at a large company that has the resources, that company might develop its own proprietary closed source version of that. And of course, Tesla would be an example of that, where it has, and Waymo and other self-driving cars, I do not believe that their source code is open source. So they're developing closed source versions of this software. And there are a lot of resources available for that because the market is large. Okay. ROS. Now, this will not run on our Raspberry Pi Zero W to my knowledge. If anybody can get it to work on a Raspberry Pi Zero, let me know. I think it's a little bit too computationally intensive. So this higher level code requires a fair amount of processing power. It will run on a regular Raspberry Pi, but a Zero I think is a little bit too weak for it. And if anybody has an experience on that, let me know. Then, yeah, so this probably won't work on your drones. Okay. The next topic I want to discuss is simulators. So we did discuss having a simulated drone last lecture. And it would be wise, if you're going to develop autonomous systems, to develop them first on simulated vehicles before you put them on actual vehicles. And that includes land vehicles and sea vehicles, ground vehicles, sorry, space vehicles and air vehicles like drones. So ArduPilot has a built-in simulation protocol and tool that you can connect your scripting to. So I would advise you to use that when you're developing your autonomous scripts, whether it's low-level Python or high-level ROS. Now, the problem with the ArduPilot built-in simulator is that the physics model is very simple. So there are additional, more sophisticated models of the system that you want to simulate to run your autonomous code on. Within the ArduPilot ecosystem, there's one called Gazebo, which simulates a three-dimensional world. So you could crash into a building, or it'll simulate mountainous terrains. And it can be very detailed. They also have physics-based simulators that simulate the physics of the vehicle. So whether it's an fixed-wing airplane or a quadcopter or a helicopter, they have fairly sophisticated physics simulators that simulate the response to the thrust of the propeller. They simulate wind. They simulate the weight distribution, center of gravity. It's all very realistic. So if you want to do autonomous scripting development, you can use those more realistic simulated drones rather than the one I showed you last lecture, which was a very simplistic one. And that can be very useful for doing debugging and development of autonomous control of vehicles. And there are also simulators to train humans, if you're interested. So if you want to be a drone racer, there are simulated drone racing programs that are like Microsoft Flight Simulator that put you as if you have the goggles on and you simulate racing a drone. So this class is about autonomous drones. We don't build and race drones, although you're going to own your drone at the end of the class, and if you want to race it, feel free. You might want to take off some of the extra weight and lighten it up, but you can try that. And so there are a complementary set of simulators that allow you to do human training, but these simulators are for training autonomous systems. Okay, so next topic for today is artificial intelligence and drones. So what is artificial intelligence? Artificial intelligence is based on a model of the way the human brain works. It's been around, the concept has been around for a long time, longer than probably since before you were born. But it's only recently that the semiconductors have been powerful enough to do interesting artificial intelligence computations. So, what was the original inspiration and what is the architecture that's implemented in semiconductors in modern 2025? So the inspiration comes from the structure of the human or mammalian brain, which consists of, in the human brain case, around 100 billion neurons. More neurons than you could simulate, which we'll get to in a moment. So each neuron is a cell that's connected to a neighboring neuron through this dendrite, and it's electrical. So the cell will send a voltage pulse along that dendrite or axon, and that voltage pulse will propagate just like a voltage pulse propagates along a coaxial cable. It doesn't propagate at the speed of sound, it's slightly slower, but it's a voltage pulse that propagates. And when it gets to the next cell, it stimulates the next cell saying, hey, start a new voltage pulse. And each cell is connected to many other cells through these dendrites and axons. And the next cell in line may or may not fire depending on what its inputs are. Those are called weights. And there's also some randomness associated with it. So if the next neuron, whether the next neuron fires in line depends on the inputs from the previous n neurons and the weights associated with that input and probability. So there's some randomness. So this is the modern understanding of how the human brain functions at a physical level. And it seems to be correct. So there are 100 billion neurons, so there are many more connections between the neurons. And there's no way to simulate that on a modern computer. Just now, barely with supercomputers, you can simulate maybe a fruit fly brain level number of neurons, because the number of neurons and the connections becomes increasingly difficult to simulate. It's exponential, I believe, in the number of neurons, the number of possible connections and pathways. Now, when a baby is born, these weights are randomly distributed, presumably, but as the baby learns to walk, speak, read, these weights get dynamically redistributed. That's called learning. So that's the biological understanding of how learning happens. So there'll be some input from the eyes. It'll go through some of these networks of neurons, and then the outputs will be write something on a piece of paper or press a button. And the weights change during the lifespan of the organism, and they change randomly, but if they change randomly in a direction that gives a positive outcome, those weights get frozen in place. So there's learning of the weights that happens. Well, changing of the weights is learning. So that's the modern biological theory of learning. And as I mentioned, you cannot simulate all those. There's no way to simulate those. So back in the 70s, computer scientists had an idea, well, let's simulate a few of them. If we can't simulate 100 billion, let's simulate a few hundred. And that's called an artificial neural network, where you create some nodes in software, and there's an input layer. In this node, X1, if it fires, it sends a signal to node A1. A1 gets inputs from X1, X2, X3, X through Xn with some weights that are not shown on this picture. And if enough of the inputs give it enough weight, if you sum of all the weights times the inputs, then it will send an output. So these weights then, each A has n weights. A1 has n weights, A2 has n weights, and so on. And then you have multiple layers, so you have a matrix of weights here. And the output is either yes or no, depending on the input. So this is an artificial neural network. It's meant to be a computational equivalent of the natural neural network. And that is what artificial intelligence is based on. So the modern version of artificial intelligence uses many, many of these, millions of these at a time. And the mathematical complexity of such a system is so large that it's impossible to realize all the different possible cases of all the different matrices in this system. So now, just like in a biological system. Now, all these matrices that basically multiply the input vector X through the output vector Y, then are varied randomly. And if the output is closer to the answer that you want, then those inputs are kept and you keep moving in that direction. That's called the stochastic method of steepest descents. So the way to train a neural network is to vary all the parameters in here, vary the matrices randomly in a certain direction in phase space. And if the output becomes closer to what you know the correct answer is, then you keep moving in that direction in phase space and you keep varying the matrices in that direction in phase space until you get to an optimum. And when you have an optimum, you freeze those matrix elements in place, and that is a trained neural network. And from then on, you can have an input vector, which gives you an output vector that you want that's been trained. That's how it works. So, yeah. So the simplest initial application of this was image processing. And so, for example, let's say you have an image. An image is a two-dimensional array of pixels, but for the purposes of AI, we can just arrange them into one large one-dimensional vector. So we take the first row of pixels and the second row of pixels and the third row of pixels, and we just columnize it. So we have one giant vector. So this is the digital representation of an image. And then you want to know, is that image a cat or a dog? So you show a whole bunch of images of cats coming in, and you vary the matrix elements randomly until the output says dog. It could be one pixel, it could be one output, dog, yes or no. So the Y could be just a single output as a toy example. So you have let's say 1,000 pixel image coming in and you want to know, is it dog, yes or no? So it's one bit going out, 1,000 inputs. And then you show it a bunch of images of dogs, and then you see if you get the right answer out, and you vary the matrix elements randomly until you get the right answer out most of the time. And then you freeze those matrix elements in place, and then you show it a new picture of a dog that it's never seen before, and hopefully it gives you, yes, it's a dog. And that's that simple. And the amazing thing is that it works. And the next amazing thing is that computer scientists don't know exactly how it works. Why it works is pretty clear. There's going to be some combination of matrices because it works for the human brain. But why you don't know how it works is a more interesting question. And the reason is the phase space, the number of possible matrices is so computationally enormous that you can never access all of them. So in fact, one of the most interesting developments in AI has been looking at how the accuracy and predictability scales with the number of elements. And that's something that computer scientists couldn't predict. So the semiconductor engineers, people like me, we kept pushing Moore's law, making smaller transistors, more powerful computers, and the industry invested in that. And then the computer scientists watched, and they just had larger and larger neural networks and trained them on more and more complicated problems. And they could not predict the accuracy of the network based on the number of nodes. That's still, to my knowledge, unpredictable because it's a very large space of possible variables. So that is a big open topic in AI is how does it work and how do you predict it and how do you improve it? But this is the underlying principle of AI, of all AI. So image recognition is the most interesting initial use case because it was computationally tractable with powerful computers back in the day. So that's the first big important part of drone AI use cases. However, there's a lot more, and I do not have enough imagination to tell you what all the use cases of AI are in drones. I can only tell you what people have thought of and what I have thought of and what has been developed so far and what I think is going to come in the future. So here's my personal list of AI in drones, short term and long term. So the most short term one is image processing, which is very well developed, and I'll show you. Another application is flight control, which is less well developed. And then a long-term application is integration of drones with large language models. So I have some Hello World exercises for some of these, not for flight controller, but I have a lot of Hello World exercise worlds for you for image processing and LLMs, which I'll get to at the end. Flight control and mission planning, I do not have Hello World exercises for you. I'll show you why in a few minutes. So let's start with the easy one, image processing. So here's another picture or cartoon of how image processing works. So to train a model, you take a series of training images, you put it through the neural network, you vary the matrices randomly, you find a set of matrices that gives you the right answer most of the time, then you freeze those matrices in place and you use those on any new images, and hopefully if you show a new image of the object that you want to detect, it will detect it. In order for that training to work, you have to feed the model many pictures of the object you're trying to detect. So they're showing here training it on an apple versus a pear versus a tomato, versus a cow versus a dog versus a horse. So you can train it with thousands of images. Once the model is fixed in place, then you have that series of matrices. And when you get a new image, all you have to do is multiply it by the matrices. Now, once those matrices are fixed in place, you can freeze that. You don't have to do any more learning, and then you can use those matrices on a computer to take the input of an image, run them through the matrices, you get an output. It's a cat, it's a dog, it's a mouse, whatever. And here's an example. Okay, so that's the principle. Now in practice, again, there are open source versions of this image recognition software and there are closed source versions. And I don't know what they use in the closed source versions. I don't know. I don't know if they use a variation of the open source versions or if they have their own. But Google, Facebook, many of the other tech companies have access to millions or billions of images. Google, especially, and Apple have their photos albums. And when you upload your photos to the Google Photos albums, they use your photos to train their image recognition software. And they actually use you to tell them, sometimes they'll show you a picture, is this John Smith or not? And you'll have a picture you've already tagged as John Smith, and they'll ask you, is the other one John Smith? And you say yes or no. So you are actually participating in training the Google Photos AI model. And not just you personally, 195 students of Peter Burke, but everyone that uses Google Photos. So that's a large set of training data, and I'm pretty sure they keep that all that information proprietary. So I don't think we have access to that as EECS 195 drone students. So the alternative is the open source models, which you can train your own or you can use pre-trained ones. And YOLO is a series of pre-trained ones where they give you the matrices already, and here you're showing detecting a handbag, a person, a car, etc. So this is free. It's open source. It's free. You can use it. So the question is, can you use it on your drone? And the answer is maybe. So even though once the training is done, the exercise, all you have to do is take the picture of an unknown object, take the data, put it through a matrix multiplier n times in a row with predefined matrices, and get an output. That matrix multiplication process requires a fair amount of computational power for interesting neural network models. Even just an element, a picture that's 100 by 100 pixels, you need a fair amount of processing power. So unfortunately, the Raspberry Pi Zero does not have that much processing power, even for simple AI models. So that's too bad for you, and so you can't do it. If you have a Raspberry Pi regular, it barely is able to do it at low frame rate with low resolution pictures. If you have a Raspberry Pi with an AI hat, which has a special processor to do these manipulations, then you can do it with a Raspberry Pi. What most drone pilots do is use an NVIDIA GPU, which is hardware much more suited to this fast matrix multiplication. So, yeah. So most of you are computer engineering, computer science majors. So you know that a CPU is a general purpose piece of hardware. It can do all sorts of calculations. And it's meant to do anything. It's general purpose. It can do arbitrary calculations. So the hardware is not optimized for any particular calculation. GPU is a semiconductor circuit that's optimized just for graphical processing, which is mainly matrix multiplication in parallel at massive scale. So NVIDIA started making GPUs for games, and when AI got sufficiently developed, they realized that running AI models on GPUs is much more efficient than running them on CPUs by a country mile. So most AI algorithms that are run on hardware that need a lot of power, which is most AI algorithms, use some sort of a GPU. So NVIDIA is the biggest manufacturer of GPU, and that's why they're doing so well financially. So they also make GPUs that fit in this single board computer type form factor. It's called an NVIDIA Jetson Nano, which most drone pilots use. It doesn't fit on our drone, but I'm just giving you an example if you want to build a bigger drone and have sophisticated image processing on board. So it's a 6-core ARM CPU. It's got 8 bits of RAM, and then it's got this 1024 CUDA core graphical processor on it. So this is hardware that can do image recognition very efficiently and more. So that's what most drone pilots use. Okay. And one of the UCI teams uses that. This is 2 UCI students, anonymous UCI students, and they use that on their giant 10-kilogram drone that they use and fly in a national competition every year. So our drones are smaller. Our drones are very small for safety and cost. So you do not have the ability to do that on our drones. There is one recent camera that was made available to Raspberry Pi Zeros, which is not part of our class because it's $70. But I have a few you can borrow if you want, and just give them back to me at the end of the quarter. And what it is, it's a Sony camera, but Sony put an AI chip on the camera. And that AI chip can run image processing with various models. And so you can do image processing with Raspberry Pi Zero with our drone. So last year I had 2 senior design teams do it, and they put this AI camera on the Raspberry Pi Zero. They were able to detect themselves. Okay, so you can do image processing on a Raspberry Pi Zero if you have this special AI camera. Okay. And essentially, it's a matrix multiplier. You upload the matrix, it's a model, and it does the matrix multiplication of the image, and it gives you a detected output. So here's an anonymous professor, and here's his cell phone, which they they call it cell phone, but nobody has a cell phone like that anymore. So that's actually my ham radio. But it can recognize even the simple model with the simple Raspberry Pi Zero camera can recognize there's about 250 different objects that it can recognize and out of the box. And you can train, so that's available to you if you want. And I do have some Hello World exercises, which I'll cover with that. If you really want to, you can train models for that particular camera to recognize specific things. So if you have an apple and you want to know the difference between a Macintosh apple and a other kind of apple, maybe you could train a model on that. I don't know what kinds of apples there are. I only know apples, but there's different kinds of apples, and you probably could train an AI model to recognize the different kinds. I think one's probably more green and the other more red, so that's one difference. But the stock models are just like person, chair, stuff like that. So if you borrow that camera from me, I do have an AI Hello World script as one of the 8 exercises. And again, because in the interest of time, I'm not going to go through all 8 Hello World tutorials in this hour. You're smart enough now that you don't need it, but they're there and they list the commands that you need to write, which package you have to install, how to configure it. There's a script that will detect a human or a calculator, and it will dump the terminal I detected a calculator when you log onto the Pi. Now, the only hard part, so this would all be very easy if you bought a Raspberry Pi, you bought the camera and put it on your desk in your dorm or your apartment, and you had a keyboard and a monitor, and it would just work immediately. There's explanations on the Raspberry Pi Foundation website. It's very simple to do. There's a Hello World on the Raspberry Pi Foundation website. So in our case, we don't have a keyboard, we don't have a monitor. So I've gone through and figured out for you how to beam the video down to your monitor from your drone Raspberry Pi over the internet, which you have connected now. And also how to do the image recognition without a monitor at all. So in principle, this exercise can be done with no monitor at all. And it'll just, you run a command on the script, you SSH into the Pi, you type in the command, and then you say, turn the camera on, tell me what you see, and the camera will dump to the terminal, cell phone, person, table. So that's one of the Hello World scripts that's available to you as one of the 8 tutorials. And then the next one is to demonstrate full autonomy, which if it detects a cell phone, it goes into land mode. So that's the simplest way that I can do image recognition for you as a Hello World and safe exercise. You take the land mode Hello World script that you already have running, and if the Pi camera on board detects a cell phone, it runs the land script. So that's another exercise that combines the two together. And that one, you can see it go into land mode on Mission Planner, or you can see it actually land when you're in the drone cage. And if you try this outdoors, try it very carefully. But landing is the safest thing I think you can possibly do. So now you have a Hello World onboard AI image processor that you can do with the hardware that you have and the training that you have and the drone that you built. And that's a Hello World, because now it could, if it recognized a car, it maybe would not land, it would take off. And it's up to you then how you want to do your scripting beyond that. One other thing that these simple open source scripts can do is recognize body motions. Like if you raise your hand, they'll recognize that. So DJI put a lot of this into their examples where initially, if you raise your hand, the drone will take off. If you lower your hand, the drone will land. So you're welcome to also try those exercises. We'll come back to flight control in a moment. I should have done this as a round. Now, the other Hello World scripts I have are the opposite. If you just want to use this little camera and you don't have any onboard processing at all, you can beam that camera down as a high definition video to the ground. So I have a Hello World script on that also, which you can do today, literally, because you should all have your cameras by now. You all have the Raspberry Pis. You don't even need the drone for this exercise. Don't you have a Raspberry Pi Zero in your kit? Yeah. So boot it up, plug the camera in, run this Hello World script, and it'll show you how to beam the video down to the ground. And so the Raspberry Pi, if it's connected on your internet Wi-Fi, you'll be able to see what the Raspberry Pi video camera is seeing on the ground. It's actually a very nice camera. It's better than the FPV camera because it's HD and it's digital. So try it. And you can just use that as a webcam. There's about 100 milliseconds of latency or more, depending on the resolution and the bandwidth of your Wi-Fi connection. But you can literally try that today as soon as you go back, as soon as I'm done with this lecture. So that's fine. So there's a Hello World script that explains how to get the video to the computer. Because, like I said, there's no monitor connected to this Raspberry Pi. So the only hard part is getting the Raspberry Pi set up with the camera without having a monitor. So you can beam the video over the internet, and you have to have some video streaming and video receiving software installed on both ends, which I walk you through in the Hello World script. It's not hard. Now, if once you're on the ground, your computer can be extremely powerful. So you can run image processing on that video that's streamed back down without the need for any onboard intelligence at the drone at all. So I have a Hello World script for that, which is complementary to the other Hello World script. You have a question?
Latency?
So we covered this a little bit when I did the video lecture. The best case latency you can get with a Raspberry Pi camera is 100 milliseconds, glass to glass. Worse. So I don't know. I don't know. It depends. It also depends on the on the bit rate of your Wi-Fi connection. So if your Wi-Fi connection is 1 megabit per second, that's not enough. If you watch YouTube in HD, you typically need about 20 megabits per second for a good signal, even with all the compression and decompression and the processing power that's very powerful on both ends of the link. So if you have a 1 megabit bit stream, no one's going to help you. You're going to be reduced in resolution. So that's different than the latency, which is if you move your hand in front of the camera, how soon does it show up at the glass on the other end? So if you have and so you're asking, what is the effect of the low processing power of the Raspberry Pi Zero on that latency? So it is significant. I don't know the mathematical relationship, but I believe that if you have a very high bandwidth Wi-Fi connection that's more than 20 megabits per second, that the latency in the HD video is about 100 milliseconds. And that's set by the camera, not by the processor. I'm not 100% sure. And if you dial down the resolution, so instead of 1920 by 1080, if you do it 640 by 480, I don't think the Pi Zero has any problem at all. But when doing 1920 by 1080, you're pushing the limits of the CPU. So even that, you're pushing limits. So you can do image processing on the ground, so you can take the cell phone on the ground. Then on the ground, your computer can send a script back up to the drone saying, okay, I detected a cell phone, go to land mode. So there's a Hello World exercise on that also. So even if you don't have the expensive AI camera, this camera is much cheaper. I think it's $15 and it's smaller. You can still do this AI controlled drone, but the AI processing has to be done on your laptop computer. And I did it with the Hello World script so you don't have to use your own laptop. Because if I had to do it for all your laptops, it would be a nightmare because some of you run Mac, some of you run Linux, some of you run Windows 10, some of you run Windows 11. I have no idea what all the packages that are installed on there. So the script I have actually replaces this with a cloud instance of a Linux server, which, as I mentioned last lecture, is free for Amazon Prime subscribers for a year and is very cheap after that. So the Hello World has you spin up an instance of Linux in the cloud, install a few Python packages like Yellow and OpenCV, get the video streaming to the cloud instance from the drone, which is already on the internet, have that cloud machine do the YOLO image processing, determine if a cell phone is detected. If it is, send a Mavlink command back through the hello world land script that's run on the cloud instance and cause the drone to land. So I did that on the ground. I haven't done it in the air yet. I invite you to do that. All those hello world scripts are there for you to use. And I would invite your feedback if there need to be improved. Okay, so that's the image processing part of drones, and you can see why it's hello world, because as drones get more powerful onboard computers, the amount of autonomy that can be implemented using the AI image processing gets much bigger. And you can imagine a situation where they're as sophisticated as Tesla computers or Waymo. And if they're not, you can imagine a scenario where they have a high bandwidth connection to the ground, where the ground-based computers are as sophisticated as the Tesla computers or the Waymos. So those are the hello world ones. Now, in the last 20 minutes, I want to talk about the more advanced topics of LLMs and flight control. So let's do flight control first. We mentioned Mavlink is a way to control the drones through takeoff, land, changer mode, but you can also through Mavlink send the direct pilot inputs on the stick. That's what Express LRS Mavlink does. But if you take a step back and get rid of Mavlink and just use the old-fashioned radio control where you're moving joysticks to tell the drone to tilt forward or tilt back, then those joystick inputs could be automated with a virtual pilot. And that would be flight control automation. And that's what this group in Switzerland did. So they used a drone that was running Betaflight. So it's Betaflight is a complementary version of ArduPilot. ArduPilot is meant mainly for GPS missions. Betaflight is meant for drone racing. So Betaflight is optimized for going fast and taking sharp turns, having low latency video, low latency RC, and racing. So the human is an integral part of that. And so what this group in Switzerland does is they replace the human with a Jetson Nano on board a drone. And they used an artificial neural network to train that Jetson Nano to put these joystick movements in that a human pilot would do. And they trained it to fly fast and to race. And they were able to show in this paper in 2023 that they were able to use this artificial intelligence pilot to fly and beat the world's fastest drone racing pilot. It has to be artificial intelligence because the conditions are dynamic. Where you take off exactly changes from time to time at a microscopic scale. The wind may blow the drone in a different way. The racing is not a predictable process that you can make an algorithm out of. So it's a human that's learning it and training it itself. So they're able to beat a human in 2023. And this is akin to the time when the IBM supercomputer played chess against the world human chess master and beat the human chess master. And that took 20, 30 years of development. For about 20 years, human chess players always beat the best computer chess program. And I don't remember exactly when it was about 10 years ago, when finally the chess computer program got better than the human. And now I believe the best chess programs can beat the best human chess players consistently. So that's an application of artificial intelligence. And this is actually fairly high level because it goes through Betaflight. So you could imagine taking that neural network and going not through Betaflight, but having it replace Betaflight. So that's another possible future application of artificial intelligence in drones, and not just quadcopters, but aircraft as well, with fixed wing aircraft. So one thing I've always wanted to do as a research project is to do this same kind of a project with a fixed wing and not with a drone, because fixed wing aircraft also have aerobatics that they can do, and they're also done dynamically, and you have to respond to the wind. And to fly an air show requires a lot of training, human training, years. So it'd be interesting to have a neural network do the same flight profile. So I'm interested in that doing that project in the future. Anyone interested? There's a senior design project for you. I think it's probably more like a PhD level project. Okay, so that's another application of artificial intelligence in flight. The one before I get to the LLMs, yeah, let's just go to the LLMs because we only have 20 minutes left. Okay, so this I think is the last frontier of AI with drones. And it scares me. And it should scare you. And I'm going to explain where we are. So, what is the completion of that sentence? Yes. How do you know? You know Star Wars. So, it's a famous line from the movie Star Wars. And nowhere else in the English language in any written textbook would that sentence appear, to my knowledge. So, if you look at every book ever written, and every email and every chat ever written, I don't think you'll ever see Luke, I am your in any of those sentences. So what an LLM does is it trains itself on all the sentences and tries to predict the next word based on the previous words. It's an artificial neural network with very, very large number of nodes that takes in a very large amount of training data, namely all of the books ever written, all of the journal magazines ever written, all the text messages ever sent, and anything else it can scour from the internet, and creates this predictive model of what the next word will be based on the previous word. So that's called a large language model. Now, obviously, there's more to it than that, but that's the basic principle. And you all know firsthand now, everyone on the planet basically knows firsthand how well it works. So ChatGPT was one of the first companies. Now there's many companies in private, there's public ones. So that's the basis of a large language model. It's predictive text. Based on input, what's the output going to be? And you know firsthand how well it works or doesn't work. So it's amazing that it works at all. And why it works is still something computer scientists don't have a complete understanding of because of the mathematical complexity of the problem. And they're still studying it. So the approach is almost like it used to be in physics. You build these models, you train them, and you see what happens because you can't predict it. But they seem to work to do some tasks very important. So I asked ChatGPT, tell me a short story about drones, and this is what it gave me. Once upon a time, blah, blah, blah. So that's what a large language model is. You need extreme processing power to run it. Even locally, you need a very powerful computer. So running it on a Raspberry Pi Zero, I think is probably out. You might be able to run a stripped down version on Raspberry Pi 5 that's very simplistic. But the commercial ones are run on ginormous farms of servers that consume vast amount of energy, electricity. Okay, so what does that got to do with drones? Well, so far nothing, because it's text in, text out. So a large language model all by itself is merely a text in, text out processing machine. The text that comes out isn't always deterministic. There's some randomness, and it's trained on all of the written words that it can get access to. There's more than training. There's also curating and guiding. And have you ever been a trainer on ChatGPT? There's also human feedback. Have you ever written a ChatGPT question that comes up? Here's two answers. Which do you like better? Raise your hand if you've done that. So they're using you as the reinforcement, part of the reinforcement learning process. And if it's a good answer, then they'll favor that particular set of matrices for that large language model. And it's not just a 10 by 10 or 100 by 100 matrix. I mean, it's a million by million matrix, and then there's millions of those matrices, roughly speaking. So you are training that machine, and not just you in the class, but everyone that uses it, which is a good fraction of the entire planet. So, okay. So that's text, but that's not got anything to do with drones other than telling stories about drones. And one other thing I should mention is the training data that you use matters. If you use low quality training data, you're going to get low quality models. And one of the interesting topics in AI is whether they get access to the scientific training data, because most of the scientific papers are not available in the public internet. You have access through UCI, but if you log in from home, you have to pay for that article. So far, they have not, as to my knowledge, struck a deal. But sooner or later, I'm imagining that a deal will be made and some money will change hands and all the scientific literature then will be available to an AI, and that trained AI will hopefully be better than an AI that's trained on non-scientific literature. Okay, so, but you're still just talking, talk. You send a message, you receive a message. You're not doing anything else other than the chat. And then when you close the chat window, it's over. Maybe saved to disk, but doesn't do anything. So the next iteration with large language models is what's called tools. And the tool is a fancy word for an API that gives a large language model access to functions it can call to do things outside of its own text context. And that thing might be read a file from Google Drive, write a file to Google Drive, access a database, check your email, send an email, read your calendar entry, add a calendar entry. So these are called tools. So the companies added capability to the LLM, and honestly, I don't know how they did it, but it was a modification beyond just an artificial neural network processing text. And they tell the LLM, if the user asks you to send an email, here's a function that you can call. And then the LML can call that function. Or it'll be another situation where they tell the LM, if the user asks you to check their email and see if they got an email from Bob, and then you type into ChatGPT, did I get an email from Bob today? Then that LLM will access the email as a tool, read your email, sort through it, see if there's one from Bob, come back and tell you, yes, there's an email from Bob, or no, there's no email from Bob. So the LLM plus the tool is called an agent. That's called an agent because it does things for you. And the tool is what it can do for you. So the problem is, so these are coming, and they're more and more coming. And obviously this presents an enormous security and safety risk. So companies are being very cognizant of how they proceed, but they're not stopping. They are going beyond just text because the application is so compelling and the profits are so compelling. So that's the sort of the state of the art now of LLM industry. So, okay. The problem, this is not specific to drones yet. I'll get to drones in a minute. The problem with this approach is that each API is different and has to be manually configured. So if you want the LLM to log in your email, you have to write an API for that. If you want to log into Google Drive, you have to write an API for that. So that's a lot of APIs if the LLM is going to do a lot of different things. And that's very tedious. So raise your hand if you've ever used an API. You must all have used APIs like in your projects. Okay. So, I mean, you use it daily in your daily life, but like, have you actually looked under the hood? So in November 2024, Anthropic, which is one of the leading LLM companies, introduced what they call Model Context Protocol, which is essentially a wrapper for all the APIs. And they call it a server, something that takes the API from your tool like Gmail or Google Drive and presents it to the LLM in a uniform language called Model Context Protocol language. So you take the API here, you incorporate it into the server, and then any LLM can use that server. Doesn't have to know what the API is. In fact, you have servers for each API that you have to write individually. And that server can live on your local machine, or that server can live on a cloud instance. And this is the protocol. So whatever the API is of the tool that you're trying to access, Google Drive, SQL database, whatever, the MCP server presents these three items to the LLM. One is resources, a list of resources that the LLM can get, files, databases, etc. Another one, the most commonly used one, is a list of tools. That's functions that the LLM can call. So a tool might be send email, receive email. So you present that as a server to the LLM, and the LLM doesn't need to worry about the actual syntax of sending an email through Gmail. So I think you see where I'm going with this with drones. But we'll get to that in a minute. And then the last one are example prompts. So this is a new protocol. It was just introduced in November, so it's barely a year old. And initially, Anthropic was the only one using it, but the other companies quickly, in the spring of this year, quickly adopted it because it makes so much sense. So now it's used by all the companies. And before we get to that, one last thing about it is the transport layers. This protocol is being sent through HTTP, which already shows you how immature it is, because you would think they would do it over HTTPS, but no, it's over HTTP. That's one thing. Or it can be sent over standard IO, which is if you have it installed locally. Be afraid, be very afraid, because if an MCP server has access to standard IO, that means they're logged on as you. That means they can do anything you can do from the terminal. You can delete a file, they can write a file, anything. So when an MCP server has standard IO access with you logged on as a user, that's a very huge security risk. And they're not regulated very well. So anyone who wants can spin up an MCP server, including me, including you. We're going to do it in a minute. So be careful when you use MCP servers. Now, Anthropic has a list of the third-party MC servers that it knows of. Well, here's one, Slack. Raise your hand if you use Slack. Raise your hand if you use Discord. You all use Discord, right? I'm sure there's a Discord server. So I think that's official and you can probably trust it, but there are thousands of third-party servers listed on the Anthropic GitHub page, and this is just the A's. So it goes A through Z. Okay. So now we're gonna get to drones. Before I get to drones, how many of you knew all this stuff before in your classes? Raise your hand if you knew about MCP servers. Okay. Raise your hand if you knew about ChatGPT. Everybody, right? So it's new. And we should start incorporating in our classes, but it's brand new. So for example, well, here's a server app store. This one is different than GitHub, and you can sort by all the different servers. It's called mcp.so. So for example, there are 51 database servers, 44 entertainment servers, 23 calendar servers, 56 cloud storage servers, 628 cloud platform servers, 71 finance servers. Don't trust them, but they're there. And the way you use them is you can run them on a desktop, which I guess we just don't have too much time to get into how to spin up a server, but you can create a server by writing code, okay? And Amazon now is offering MCP servers as part of its cloud package. OpenAI just last week decided that if you have developer mode in ChatGPT, that you can connect to a third-party server. And I tried it and they wouldn't let me because they said it wasn't safe. So there's another OpenAI way. So it's a brand new protocol that's taking off like crazy, and all of the LLM companies are going to eventually use it, but it's very immature and very insecure. Which leads me to drones. So there is a server, MCP server for Mavlink, and it's available on GitHub. And unfortunately, it only has 4 functions, which I'll show you. So it doesn't have all the Mavlink commands. So a good senior design project would be create an MCP server for all the Mavlink commands. And if anybody wants to do that for their senior design, please come talk to me, because that'd be way more interesting than a lot of the senior design projects that are being done. Because a lot of people use it. So you get to use it in my class. And, oh, it's 45, I have 5 minutes left. Okay. So let me show you the final in 8th tutorial is a Hello World LLM drone tutorial. So you log into ChatGPT and you say flip a coin. If it's heads, send the drone north 5 meters. If it's tail, send the drone south 5 meters. So I have that server running for you through Hello World. And since I have 5 minutes left, I'm going to show you some details about that if you want to implement that. In fact, it'd be easy to implement it on the virtual drone that Calla flew last week, because that'd be very safe. If you do it on a real drone, yeah, we'll get to that in a minute. So anyways, this is the mechanics of MCP servers. You have to have some code running somewhere on some computer somehow. The LLM connects to that code, and then that's one interface. We can easier with a picture. So this has to be some program running on some computer somewhere. And the LLM has to be program running on a computer somewhere. And whatever it sends it to has to be running on some computer somewhere. So this server has to be written code running on a computer somewhere. Usually, okay, so what I'm going to propose for you is to run this on an Amazon or DigitalOcean cloud instance that you spin up, which is very cheap. So spin up a Linux server in the cloud, log in, run the Hello World tutorial instructions. It'll create a server for you. That'll give you an IP address that the LLM can connect. And the other IP address will be your drone. You should take a picture. So, and you can use LLM. ZotGPT is no, they won't let you do it. I asked them, they said they haven't got that far yet because it's new. And even ChatGPT was difficult. So if you want, you can use your own LLM server. The ones that do work are Claude Desktop, Windsurf IDE, Cursor IDE. ChatGPT has a desktop application. Raise your hand if you've used any of these 4 desktop applications. About half of you. So these will run it without permission. So let's look at what it does. And I just got this done last week. And it's your last Hello World assignment. So I forked that code for you and created a fork of it with detailed instructions. And here they are. Here's the quick start. Here's the blah, 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 blah. But these are the available commands that the server exposes for your drone. So if you run this server, follow the Hello World tutorial instructions, these are the commands you can send to your drone. So you can say ChatGPT, flip a coin. If it's heads, arm the drone. If it's tails, disarm, and so forth. It's pretty restricted. As you saw, Mavlink has 255 different commands. PyMavlink encapsulates them. So this is basically a Hello World MCP server that somebody wrote that I forked for you. So your last exercise, optional exercise in this class, is to connect an LLM, either ChatGPT or another one, to a server that you create using the tutorial. Connect the server that you created to the drone, which has an IP address, and have your input to the ChatGPT control the drone. After you do that Hello World, please be very careful how you use that technology in the future.